Associate Professor in the Department of Physics at IIT Ropar. After completing his doctoral work from Physical Research Laboratory in Ahmedabad in 2005, he moved to University of Southern California to carry out postdoctoral work in the area of geometric phase in open quantum system. In 2007, he started working with Professor Paul Broomer at the University of Toronto. Shubhrangshu is interested in the areas of physical modeling in quantum optics, nanosystems, and decoherence in physical systems, and he has several publications in these areas. So his title is Quantum Synchronization, Entanglement, and Their Common Origin. So without further ado, I would hand over the floor to Shubhrangshu.
Thank you, Chiranjeev, for your kind introduction. I must thank the organizer to invite me to this QIQT. It's a regular annual event. I think it is a very good initiative from IISER Kolkata. So let me share my screen first. I think it is visible to all of you. Okay, so my talk is okay. I will talk about quantum synchronization, entanglement, and if there is any common origin of two. This work is with my colleague, Dr. Ashoka Biswas, and my two students, Manju and Devender. So because the quantum physicists live in a linear world of Hilbert space, and I think, introduce what does it mean by synchronization, because this is something that we often do not read well in our studies. So I will discuss what is synchronization first, and of course, what is not. And then I will discuss about that how two oscillators can be synchronized in quantum regime, and then I will try to relate it with entanglement. So let us start the classical concept of synchronization. It all started with Huygens' famous observation, where he found that if two pendulum clocks are fastened to a beam, I hope you can see the beam in this sketch. And generally, the two pendulum clocks do not need to have the same frequency. In that case, after some time, let us call it asymptotic limit, they will start oscillating at the same frequency. And it is irrespective of their initial conditions. And you can easily understand that these two clocks have some kind of weak coupling through the beam, because the beam vibrate, and that is why they exchange energy with each other. And the frequency at which these two pendula oscillate is different from their original frequencies. Looking at this particular structure, the physicists will often look forward to the coupled pendulum problem. It looks like to us, it is the same as a coupled pendulum problem, because in that case also two pendulums are connected by a spring, and they keep on exchanging energy with each other, and they finally end up with a particular frequency. However, we must be careful. Let us try to understand what is the coupled pendulum problem. They are governed by these particular equations. X1 and X2 are the displacement of the pendulum from their equilibrium position, and K denotes the coupling constant, and the corresponding acceleration is proportional to the displacement. So is this a synchronization? I would say no, because the coupling between them is linear. And that is why the superposition of the solutions, these two equations, is also a solution. That means if we deviate the two modes, if we do not start with the in-phase mode, let's say, if we start with a mixed superposition state of the in-phase and out-of-phase mode, it will not come back to the original mode. It will never end up with a common oscillation at the end of the day. If it is in phase mode, it will remain so. If it is in out of phase mode initially, it will remain so. And if it is in a superposition state, then it will start in having some kind of Rabi oscillation kind of energy exchange between the two modes. Asymptotically, it will not end up with a common mode. And also the dissipation dilutes the motion. So if you that let it oscillate by its own, after some time there will be dissipation like air drag, the friction at the suspension point, and ultimately they will stop oscillating. So this is of course not synchronization. Synchronization is rather the adjustment of rhythm of oscillating objects due to their weak interaction. I already said that the coupled pendulum problem has a linear coupling between the two. I am here saying that there is a weak interaction between the two, yet they are non-linear. And this non-linear interaction and dissipation are the two most important ingredients for spontaneous synchronization of the two oscillators. So when I say nonlinear interaction, it supplies the energy, and dissipation reduces the energy of the system, and there must be a balance between the two, and ultimately they start oscillating forever in presence of the both. So dissipation will not ruin the problem there. There are three main features of synchronization. One is the oscillators are self-sustained or autonomous. It is said so because there must exist a source of energy. In the case of this oscillation, it is nonlinear interaction that supplies the energy. It does not depend upon the initial conditions, like no matter whatever their initial oscillatory stage is, the two oscillators ultimately will end up being synchronized, and it is stable against small perturbations. So this is an important aspect of synchronization. So let us summarize the important features. So when two oscillators get synchronized, their frequencies that one can measure, they become equal, even if their original frequencies are slightly different. And there is a synchronization region, as you can see. For example, the two frequencies, small f1 and small f2, are different. Even if so, the delta f, which is the frequency difference of the two oscillators, when synchronized, is 0. That means that means to have the synchronized frequency the same of the two oscillators, one did not have the same frequency at the beginning. However, if delta f, the original frequencies of the oscillators, become really much larger, you cannot get synchronization, of course. Well, that is too much of expectation from this kind of system. Okay, so that means, as I understood, that there must be some kind of a Plateau-like structure in the frequency interval plot. The amplitudes become stable. Any nearby trajectory is attracted to the limit cycle. So if I say there is a phase space where y means x dot, particularly the momentum space, then in the position momentum space, there will be a closed circle, closed loop. Let me not call it a circle all the time. So this is called the limit cycle. So if you start from an arbitrary value of x comma y, then it will slowly slow down to the thick line inside. And if you start from inside the limit cycle, then also it will slowly increase its x and p, and then finally merge with the limit cycle. So this is also understood from the time domain plot. You can see that the value of x is chosen arbitrarily from away from this horizontal x-axis. Even then, at long time, after long time, at the asymptotic limit, they start oscillating very nicely. Okay, this is for the x value for one of the oscillators. the other oscillator will follow the similar times, time variation. So ideally, that even if there is some kind of perturbation, the system will come back to the limit cycle. However, in the linear system, just to understand the issue, which are of, if it is conservative, then it will actually retain the total energy constant. That means that it will be a nice looking circle in XP domain. So for example, for an oscillator, the energy is effectively X square plus P square, and it will be always a circle. And in that case, it will remain the total energy constant. It will not ultimately go to a particular limit cycle in this case. Okay, so if you perturb to a different smaller value of X, it will remain in a corresponding cycle separately. And if it is a dissipative one, then it will ultimately boil down to a value X is equal to 0, P is equal to 0 point. That means there will be no limit cycle. It will, its motion will cease to exist. So that is the major difference for a linear system like coupled pendulum problems and with the nonlinear system. So I am also, their phase difference will remain constant. So if you perturb, the phases will take new value and it will not be the same as before. So look at the plot B here, that if I have a perturbation, that means the black dot has gone out from the limit cycle, and when it will come back by reducing its energy through dissipation, through relaxation, it will come back to a different point on the phase space on the limit cycle, and the different point will differ from the original black circle by some phase. So the phase will change. So in fact, the phase difference will remain constant after perturbation, but the phase will change. So in the force damping or damped oscillator problem, for example, where you apply a periodic force on an oscillator, the phase depends upon the driving force. We often plot the phase with frequency of the driving force. Okay, there is a phase spectrum for that. In the current case of synchronization, phase is a free variable. So if the system is a limit cycle, any phase is allowed. So let me start with the standard features, little more details. Consider an oscillator which has a total time dependent phase phi t and a driving field which is having some amplitude epsilon and a time dependent phase phi et. This phi and phi et are functions of frequency and some initial phase. Now, if I consider that the oscillator is already in a limit cycle, because I am assuming that epsilon is a very small number, and that is why it does not perturb the amplitude of the oscillation, then at asymptotic limit, the oscillator will get frequency locked at a frequency capital omega. This capital omega is not necessarily its original frequency, small omega 0. However, this value will be equal to small omega. In this case, when you have a driving field driving an oscillator, single oscillator. And you can see this from the first plot on the left side, that if you increase epsilon, there is a larger range, a bigger plateau on which this frequency locking will remain so. So that means that I can see some kind of triangular look on this plot, and this triangular shaded area is often called as Arnold tongue. It looks like a tongue. However, also the oscillator will get phase locked with the drive. Please remember that though it looks like to us that phase and frequency are almost the same, if it is frequency locked, it should remain phase locked. It is really not so. Actually, frequency is nothing but derivative of phase with respect to time. And when I say it is phase locked, phase may remain constant, but its derivative may not remain constant. So that is why frequency locking and phase locking are more or less very different concepts. Okay, so the oscillator also gets phase locked, and the phase difference will remain constant at the long time limit. And it will be in a constant value phi 0. This phi 0 and the phi 0 for the oscillator are little different. This phi 0 depends upon the initial phase of the field, and the phase difference delta phi, that will depend upon the frequency difference between oscillator and the driving field, the so-called detuning. So if I put some kind of perturbation, we go to the neighborhood of the limit cycle, and then we can in fact make some kind of equation for the phase of the phi of the oscillator. And this phi follows this kind of equation, while capital Q is nothing but the force, perturbing force. It is proportional to that. So if I take a rotating frame in the frequency of omega, then what I will see that there I can get some kind of equation for the phase difference between the two, and that will be looking like that, while Q is a periodic function. And because of this periodicity, the equation becomes nonlinear. So for example, Q is a sine function, and sine function is nothing but a series of delta phi cube, delta phi to the power 5, and so on. And that is why this is essentially a nonlinear equation. This form of the equation is famously known as Adler equation. So because this function is periodic, Q is periodic, there must exist a minimum and maximum. And if it is happening that on the right hand side the value is 0, then I can say that delta phi becomes constant. So that means if it is periodic and if it crosses 0 line of this variation, then there must be two values of epsilon Q, minimum and maximum, within which it will become 0, and the detuning will be equal to that particular value, and by that time delta phi derivative of delta phi vanishes, and that means that it becomes phase synchronized. The phase difference becomes 0. So this is nothing but a one stable fixed point. Okay, in the asymptotic limit, the phase synchronization happens in this way when there is one single oscillator, and it is happening in the neighborhood of limit cycle. We assume that it is already near to the limit cycle. That means we are not much bothering about the amplitude of the oscillator, rather the phase of the oscillator. Now, if I have two oscillators, what will happen? I can get two sets of Adler equations like that. In terms of the phase difference, we also can get similar looking equation, where delta phi is the phase difference of the two oscillators, and omega 1 minus omega 2 is their corresponding detuning. And in fact, also we can find a stable fixed point, and there will be two frequencies at which the phase synchronization Okay, so now if in the neighborhood of the limit cycle, if I give a perturbation to the oscillator, then we can get an equation of the phase of the oscillator, and where the capital Q is proportional to the force that is given by the driving field. And this capital Q is a periodic function. And if we can understand that this is like a nonlinear function, nonlinear equation, because capital Q is periodic. In the rotating frame, in the frequency of the oscillator driving field frequency, this equation becomes an equation of the phase difference between the oscillator and the driving field. And this is nothing but, this is known as Adler equation. So Q, because Q is periodic, we can say that there must be a maximum value and minimum value, and between which it may cross a zero line. It may pass through a point when it becomes equal to the detuning omega minus omega 0. So if it is so, then the derivative of delta phi vanishes, because right-hand side vanishes. And at that particular parameter domain, your delta phi becomes constant. And we can say that this is nothing but equivalent to phase synchronization. In the case of two oscillators, we can again get two sets of equations, as I mentioned for single oscillator. And in terms of the phase difference, the equation becomes like that, where Q is again the periodic function. This is also an equivalent Adler equation. And as before, we can identify a stable fixed point, the value of delta phi 0, for which the right-hand side vanishes, and there will be phase synchronization because delta phi becomes constant. And this happens at two different frequencies, which are different from both omega 1 and omega 2. So this extra part, I mean, the difference between the observed frequency capital omega at which synchronization is happening and the original frequencies, that extra part is proportional to the amplitude of the field, I mean, amplitude for the coupling between the two, and the periodic function, the values of the periodic function at that around that stable points, plus minus delta phi 0. Now, if I have many oscillators, then Kuramoto had given a wonderful, most discussed model, the so-called Kuramoto model, where he had assumed that periodic function to be the simplest one, the sine function. And this is function of the phase difference of the two oscillators, jth oscillator and kth oscillator. If there are n number of oscillators, then we can say that there can be some kind of degree of synchronization, which is nothing but an average phase. So if I say it is nothing but the average of e to the power I phi j, all the phases of all the oscillators. And this is suitably proposed by Kuramoto. Let us quickly carefully see what it is. If all phases are equal to the psi is the average phase, then we can say that the sum gives you a capital N, because and then the right hand side becomes e to the power I psi. That means the value of R becomes 1. So let us understand it in this way, that if all oscillators are phase synchronized with each other, then they will fully coherent. And if it happens that all phases are random, then the sum over so many phase terms, oscillating terms, when n is very large, this sum vanishes, this average value vanishes, and that is why R becomes 0. And that is why it will become like phase desynchronized. Okay. However, there exists a critical value of epsilon above which you can get a phase synchronization. There is a nice review paper on only the Kuramoto model, and that was in Review of Modern Physics. Let's now start talking about the quantum domain. As I already said, the nonlinearity and dissipations are the most two important ingredients to achieve synchronization. If I start with a single oscillator in quantum domain, The van der Pol oscillators is the most studied one, and it has a nonlinear dissipation and a negative damping. Let's get the equation first, then we can easily understand what is what. Let us understand minus gamma 1 term. Because of the minus sign, this is not necessarily the damping the way we understand. It is a negative damping. So the minus gamma 1 actually supplies energy to the system. And gamma 2x square is a nonlinear term because of x square. And because of the plus sign, it gives you the dissipation. And this actually reduces the energy from the system. The system has an unperturbed frequency omega 0 and a driving part capital omega d. Quantum mechanically, this can be rewritten in this fashion, where B dagger defines that you are supplying energy incoherently, and B square takes care of that, the fact that you are actually taking 2 photons out of the system, 2 quanta out of the system, that is also incoherently. The coherent part of the oscillation, coherent part of the system is given by the detuning delta between the omega and omega 0, 2 parts, and capital omega d is nothing but the driving part. If gamma is larger, that means you are supplying too much of energy. Then you are taking energy out of it. That means there will be many energy levels that will be populated. And this is equivalent to the classical limit. This is equivalent to the fact that as if you are increasing the effective temperature of the system. And when gamma 1 is much smaller, that means you are actually dissipating more energy via the B square term, the gamma 2 term here. Only a few energy levels will be populated. Then it can be considered as a low temperature limit. Beta, and you can easily understand here that the beta, this is a nonlinear equation of beta. Take the amplitude part and the phase part, get their equations, and the phase equations looks like an Adler equation, where you can see the sine phi is nothing but that periodic function, and there is a detuning term. This is exactly the same as the old Adler equation. And if you plot this phase space trajectory, that is nothing but the real beta, imaginary beta plot, XP plot, then it looks like a very nice looking limit cycle. And all this is both in the classical and quantum domain. However, there is no frequency locking, because the observed frequency is not remaining constant for a range of delta. Rather, it is a function of delta. As delta increases, omega observed increases. That means this becomes a straight line around delta is equal to 0. It is not making a plateau. So this is the problem in the quantum van der Pol oscillators. Now let us go to the 2 oscillator problem. In 2 oscillators, we can define 2 variables, Q minus and P minus, while Q minus and P minus are the difference between their position and momentum quadrature. So as we understand that, well, they will become synchronized if Q minus vanishes and P minus vanishes asymptotically. I mean, I am not considering the phase part or amplitude part of them. So that means when I say Q minus and P minus both vanish, we say that this is equivalent to complete synchronization, not the phase synchronization only. In Murray, in this particular paper, Murray and his co-workers had given a measurement of this complete quantum synchronization. They considered the RMS values of Q minus and P minus, and the not RMS value, rather Q minus square average and P minus square average. This will become the uncertainty if Q minus average and P minus average vanishes. In any case, this is the measurement they are talking about. Let us try to carefully understand this, that if Q minus and P minus vanish both, then SC becomes, it tends to 0 classically. But because they are quantum mechanical operators, Q minus and P minus can never be 0 altogether. There is a lower limit of them, of this expression in the denominator due to uncertainty principle. And that is why SCT has an upper limit. Okay, so that means that in the reference frame of the expectation values, so if I write down Q minus as a sum over the mean values and the fluctuation, then we can get the true quantum mechanical measure of the synchronization, which is written in terms of the quantum fluctuations only. So, and this has an upper limit, which is 1. Let us quickly try to understand this one here. This SQT is a valid measure only if the system Q minus and P minus are 0. That means if the two classical limit cycles, if there is a limit cycle in the sense of mean values of Q minus and P minus, when we treat them quantum mechanical. So to study SQT, what we do? We find out first the limit cycle in terms of mean values, and if it attains a limit cycle, and then we only consider whether SQ remains lower than 1 or it increases, it becomes more than 1. What to do with phase synchronization here? You define the fluctuation part like this: BJT minus average value of it. This is a complex number. You write it in terms of amplitude and the phase, and this phase we are talking about. If I consider this as a complex number, you can also rewrite it in terms of delta Qj and I delta Pj. And then we can say that the non-Hermitian part of the delta Bj will give rise to a function called SP, which is nothing but the delta P1 minus delta P2 whole square average inverse of that. So this is represented in terms of the non-Hermitian part of the delta Bj. Okay, this is the point. So when I say that the SPT is a measure of phase synchronization, we only look at the imaginary part of delta Bj. And it becomes relevant only when oscillators are synchronized on average. That is when they attain a limit cycle. There are few works. What Murray did in his paper, he used this particular form of complete synchronization and phase synchronization and studied whether a particular system that is given here gets synchronized or not. This is nothing but two optomechanical setups. Let us try to understand. Consider one of them. You can see there are two mirrors. There is a cavity. There is an optical mode. This cavity is driven from the bottom by laser driving, and that one of the oscillators, the upper one, is oscillating, and it is oscillating in a frequency ω1. The consider the second oscillator optomechanical setup. It is the same. So the two mirrors, which are now coupled externally by some coupling constant mu. You can consider many of them in this way. There can be n oscillators the way it is proposed here. If we consider just two of them, then we can see the corresponding Hamiltonian written to be in this way. So there is a nonlinearity in their position quadrature, and the nonlinearity is proportional to the AJ dagger AJ, which is nothing but the energy content in the jth mode of the cavity. And there is a direct coupling between B1 and B2 by an amplitude mu. Okay, this is the model. And in this model, these people have found that, well, the complex synchronization does not happen. It takes a value of the order of 0.2 or so, and there is a phase synchronization which is taking a value of the order of 0.1. More importantly, they tried to say that this, if I change mu, then there is a range of mu through which average value of the synchronization parameters, time averaged values, they follow the same variation as with the quantum discord. So they try to say, well, that means quantum synchronization and quantum discord go hand in hand. They could not find any entanglement because negativity became 0. But they said that, well, there could be some kind of correlation between the discord and synchronization. There is another paper, 2 years later, they considered 2 van der Waals oscillators. And they are coupled with each other. And you can easily see the coupling constant to be G here. B1 and B2 are the corresponding annihilation operators. They actually calculated the same thing. They calculated the synchronization measure, number 1, and they also calculated the mutual information. And they found that their variation with the detuning are the same. And if the variation is looking like the so-called Arnold tongue, the way I have told you, if you can see the Arnold tongue behavior before, let me show you once back again for understanding. You can see the Arnold tongue is in the frequency axis, the detuning axis, and the axis of epsilon, the coupling constant. Okay, the driving field amplitude. So this is a Arnold tongue in this frequency amplitude domain. Here also it is shown so that you can see the driving field G and there is a detuning. Around a detuning to be 0, there is a large value of mutual information and synchronization measure is also very large, and they are behaving similarly. So they said that, well, mutual information can be a nice synchronization weakness. However, there is a problem. Okay, in the previous work, I told you that discord can be a measure. Discord can be a marker for synchronization. Mutual information can also be a marker for synchronization here, according to this pupil. The main problem here is that why they should do so. I don't understand if there is any intuitive explanation between the two. I am plotting completely 2 independent parameters and looking at their similar behavior, we should not say that they should be related with each other. There is no analytical link between these 2 parameters, synchronization and mutual information, or synchronization and discord. We rather said in this work that I will be describing soon that, well, there could be some relation between the synchronization and entanglement. Entanglement is little different from mutual information and discord. So if 2 oscillators follow that Q minus, P minus tending to 0, we say that they are synchronized. And if they follow Q minus tends to 0 and P plus tends to 0, that means we can say they are EPR correlated. In the language of synchronization, we say that they are anti-synchronized. So that is why the Murray and his group said that synchronization and EPR entanglement should not go hand in hand. But this intuition is based on the mean values of these variables. We must treat them in terms of quantum uncertainties. So what we will do, we will try to define entanglement in terms of the uncertainties. And we already have found that synchronization is rather quantified in terms of uncertainties. So let us start what is known for entanglement in terms of uncertainties. Entanglement between 2 bosonic modes can be understood in terms of the uncertainty relation like this, which is obtained from the original uncertainty relation, which is given here. So if I say delta Q minus whole square plus delta P minus whole square greater than equal to 1, take the Paris criterion for partial transposition. This boils down to this one. This particular equation, delta Q minus whole square plus delta P plus whole square, it is becoming equal to 1. This is the separability criterion for Gaussian states. If it is violated, then as Duan, Chirac, Zoller, and our Indian scientist Professor Simon, they have shown that if this equation is violated, then the Gaussian states can become entangled. It can be rewritten as in terms of a stronger criterion that we will use in this work. We call it ED, and this can be greater than equal to 1/4. So if this product becomes less than 1/4, we say the two oscillators are entangled. So now we have a complete synchronization measure and bosonic entanglement criteria. And it is the same Heisenberg uncertainty principle that sets an upper limit for synchronization and a lower limit for entanglement. And both are written in terms of second order moments of a set of joint quadratures. And because we know that in complete synchronization, the oscillators are oscillating suitably, and they can be defined in terms of Gaussian states, and the Duan-Chirac criteria, Simon's criteria, they are good for Gaussian states so far entanglement is concerned. They are both necessary and sufficient. So now, if I say that two oscillators satisfy both the, violates ED inequality and satisfies the synchronization criteria, we can say that, well, they are both of them, both entangled and synchronized. Now, we can easily see that they are originating from the same uncertainty principle, and that is why the similar type of EPR correlations. So that is why we say that they are originated from the same type of quantum correlations. Our first model is like, again, two optomechanical setup where the two oscillators are directly coupled. The two oscillators are not coupled. Rather, I should say they are not coupled. They are in the middle of the cavity modes. However, there is a tunneling between the two cavity modes via the J. And the two oscillators, two cavity modes are also modulated. And this paper is published this year. This is a joint work with our students Devender Manju and my colleague Ashok. So here oscillators are not coupled. That's the major difference I wanted to emphasize. We have found that the average value of the positions and momentums, they follow the same time variation at long time limit. And we have calculated SQ and ED. We can see that on average SQ remains close to 1 and ED remains less than 0.25. That means it violates the Simons-Duan-Chirac criteria. And they follow this kind of pattern also. And we found that, yes, when ED is much smaller, maybe presumably less than 0.25, SQ is much larger. And when SQ vanishes, ED also vanishes. I mean, SQ becomes close to 0, ED also becomes larger than 0.25. And there is a large detuning domain, detuning between the two oscillators, during which SQ and ED follow, the similar pattern. Okay, so they appear together, they vanish together. And it is happening for a large detuning regime as well. Let us go to the model number 2 also. The similar thing we actually found out. And in this case, the two oscillators are little different. One is in the middle of the cavity and another one is one of the mirrors. And that is why two oscillators are always coupled. And in this case, the coupling constant has a Q squared term also and a Q1, Q2 term. So there is a direct coupling. If there is enough number of photons in the cavity, then G3 A dagger A can be large enough to couple them stronger. In this case also, we found that the average values of their positions follow the same pattern, and that means they have attained a limit cycle, and also the ED becomes much less than 0.25 and SQ becomes close to 1. And that is why they are near complete quantum synchronized and also quite enough entangled, because they violate the criteria much strongly. And they also follow the Arnold tongue. You can see that the amplitude of the driving field and the omega d, the detuning, are shown here along two axes. And this is the plot for the synchronization, and this is the plot for the entanglement. When SQ becomes close to 1, for example, in the top of the plot, the ED becomes much smaller than 0.25. So we say that both sync and entang go by Arnold tang. Now we can see that, I mean, a little bit of manipulation of the calculus. I mean, these expressions, we found that delta Q minus whole square has a lower and upper limit. And when they are different, then we can say, when they become equal, we can say that that is the parameter that corresponds to the parameter regime at which both entanglement and synchronization appear together. We have parameterized this in terms of some number k, and this k is nothing but the maximum value minus the minimum value of the limit of delta Q minus whole square average. And this also follows the Arnold's tongue pattern. And we have seen that in detuning, if I change the detuning of the two oscillators, SQ and ED also go hand in hand. And we rewrite this SQ expression in terms of ED. We find out that if ED becomes smaller, then SQ increases. That means if the oscillators become entangled, they tend to become near complete synchronized. If there is no entanglement, there is no synchronization, and there exists domain when there is no entanglement but synchronization. So but however, that synchronization is not the complete one; it is the incomplete synchronization. So this observation suggests that, well, entanglement may be considered as a sufficient condition for synchronization. So what we saw finally, in quantum regime, the limit cycles means we need to consider the mean values of the quadratures. And when they attain the limit cycle, the complete quantum synchronization corresponds to equality sign of the uncertainty principle. And if I look through Sirac-Simon eyes, entanglement can be a sufficient condition for complete quantum synchronization. Okay. And in optomechanical models, we actually needed the amplitude modulation to achieve the both. However, we have not considered phase synchronization, and also we have not considered many oscillators. So we expect more PhD students should come to help us in this field. Thank you. Thank you, Chiranjeev, for giving me extra time.
Thank you very much. So it is open for questions now. You can switch on the video.
See, Chiranjeev, can I ask one question? Yeah. See, Shubhrangshu, very nice talk.
Okay.
You know, there was some experiment, you know, QIQT experiment in IIT Kanpur.
Yes, yes.
To cold atoms. So what was the measure there? What kind of measure they took? I know they took some other parameter.
If I remember, I think they considered Husimi Q function. I think they are not for oscillators, rather spin systems.
That was spin system. Okay. Yeah. So this is very interesting. And this, you know, connection between entanglement and synchronization. But you know, I have a bit of problem here to understand. So-called ferromagnetic system.
Sorry?
Right? Ferromagnetic system. In ferromagnetic system.
Okay.
Like say off kind of thing. They are all in the same direction, right?
Yes, right.
We know that there is no entanglement there because it's a separable. So then would you call it synchronized behavior or no? Because if
no,
you
here we said that if we define if we want to characterize entanglement in terms of that joint quadratures, not in terms of different measurement like negativity or other things, only in terms of joint quadratures, we can say that they go hand in hand. I think we should understand from that point of view, particularly for bosonic systems. Yes.
I think what you are telling is look at the perturbation, you perturb that system, right? And then look at the delta P from the perturbation perturbed system and then check out that, right?
Right.
the excitations like magnos, they could be, entangled.
Yes, right. Yes.
Yeah, thanks.
Yeah, thank you.
Yeah, any more questions? Ranjit Singh has a question. Ranjit, just yeah, you can switch on your video and ask the question.
Yeah, I have issue with my video.
Okay, fine.
Okay. Thank you for your talk. One question: are two oscillators interacting in some nonlinear medium? Because they have different frequencies, and linear interaction will be negligible due to phase mismatch. So my question is, are these two oscillators interacting in some nonlinear medium or linear medium?
They interact non-linearly. If you carefully look at the Hamiltonians that we have considered, you can see the non-linearity here. For example, in our model 2, there is a Q squared term, and they are also coupled via Q1, Q2 format. So if you carefully look at, if you make a square of these expressions, Q squared, Q and Q1, Q2, you can make a square of them, and you can see the nonlinear interaction between them.
Okay. So in case of nonlinear interaction, a new particle or new photon should emerge because two particles are interacting. So in your case, what
Yes.
is
Yeah, that's a nice point of view. However, I don't think that there is any, I mean, this is, I mean, there is a decay in the system, of course, the photon will come out of the system. However, the nonlinear, I mean, this is fed by the cavity mode. And that is why the energy is balanced. Okay. So it is really not giving rise to, how should I say? There is a, let me put it again, that if energy is fed by the cavity mode, there will be also a competing dissipation form via the dissipative mode. However, the dissipation is linear and the cavity feeding is also linear. The feeding is linear. The number of photons, I am not getting any additional ones. So, however, this is not a conservative system, we must understand. So in long time limit, they maintain their total energy, but what I should say, because of nonlinearity, they are maintaining the synchronization altogether. The interaction is nonlinear. In the Van der Pol oscillator system, for example, they also dissipate non-linearly. In this case, we have linear dissipation.
Thank you.
Okay.
Okay. Any more question? Right.
I have a question.
Okay.
Yes.
So, the analytical expression for the quantum synchronization, you gave that condition.
Yes.
So why is that the expression? So why are you taking that as a criteria, whether there is an
This is, I should not say I have taken, this is in this paper, but I should justify it. This is, I also could consider the I need not take the inverse of this expression. I could also write Q minus whole square plus P minus whole square average. Okay, this is in terms of a, formulated expression. Where if it says that if Q minus P minus both vanish, SC tends to infinity. In quantum mechanically, not to infinity, rather to a finite value. Okay, that is it. I mean, we say that if SC is extremely large, that says that it is synchronized, and if SC is 0, that means it is not synchronized. In classical way, 0 to infinity is the limit, and because we understand that if something is very large, infinity or a very large number makes the right meaning of it. That is why it is taken inverted. It is inverted in this way. Okay. If I say that this is 0, SC is 0 means complete synchronization, it does not, I mean, create the right click in our thinking process.
Okay.
Mhm.
Okay. Okay, if there are no further questions, let's thank Shubhrangshu once again. Okay. Thanks, Shubhrangshu. for
Thank you
giving-
very much, Ilanji. Thank you.
Okay, thank you, sir. So there is a short announcement for the attendees. There will be a tutorial on the basics of quantum foundations and information. So I would request all of you to please join in. It will be from 3 to 5 p.m. Then followed by a talk by Stephen Girvin from 7 to 8 p.m. That's it. Thank you.